All right, so I'm now recording. Let's get going. So one thing I do want to know about the recordings, like they take a little bit to like get processed and uploaded. So when you go to the WebEx link, there's like previous recordings. It takes like they don't show up until like the end of the day. So if you're looking for them, you basically wait till like the afternoon. Anyway, okay. So where were we last time? We finished off by demonstrating the existence of a very particular subspace. So we proved that in a vector space, every subset has a subspace associated with it. Particularly, there is a smallest subspace that contains E. And we call this the span of E. Okay. So by its construction, so right, last time we went through all this delicious proof here, right, and specifically this means that the span is a subspace that contains E, so that any subspace that contains E must contain the span. And we noted that this is pretty much almost purely set theoretic until we get to the last bit where you have to actually use the definition of what a span is. By construction, we immediately get a whole bunch of stuff is true. Right. Because the span is the smallest subspace containing E, all of the following things that I just wrote here are instantly true, and we don't need to prove them. It's by its definition, all of this stuff right here is true. Right. And so statements like that in mathematics, we usually refer to those as corollaries, which I highlighted right there. But I also want to stress that corollary is the incorrect pronunciation of this. The correct pronunciation is corollary. Everyone says corollary, but apparently the right way of pronouncing it is corollary. When I was at a conference, I was talking to a guy from England, and somebody said corollary in front of this person, and they got very upset about this American butchering of the King's English. So corollary is the right pronunciation. And he went off on a tirade about why it is, and he was explaining. It was great. And see, he made the fundamental flaw though that he thought that there are rules to this stupid language we use. So he looked up. But anyway, so if you see this, you want to impress everyone, use a corollary instead. But anyway, so these are statements in math where right, we don't need to write a formal proof for this. This is immediately obvious from definitions that we've set up, or they're just equivalent to something we've already proven. So for this one specifically, right, because span is the smallest subspace containing E, all of this stuff is immediately true, right? E is contained in the span of E, right? It's a subspace that contains E. Boom. It itself is a subspace, so it's closed under scaling and addition. That is by its construction. Given any subspace that contains E, well, span needs to be contained in there because, again, it is the smallest one. Right? We prove that a subspace with these properties exists. And furthermore, if you want to prove that something is actually equal to the span of something, right, what do you need to do? Well, you just need to show that the set you think is the span of something contains E, is a subspace, and is contained in any subspace that contains E. So prove it's the smallest subspace containing E, then boom, automatically S needs to be the span. Okay. So these four facts are immediately true from this definition of span. So a little bit later today, we're going to prove the span of a set is a different, maybe more natural characterization. But trying to prove everything I'm about to prove using that definition is a nightmare. So we will see that there's a more like vector space oriented proof of span that's more related to the stuff we've been working on. Right? Because, like I said, this definition that we've been working with is very set theoretic. And the reason I chose this is because it just the proofs are so much easier, and and it implies the characterization that everybody uses for span anyway. So let's just go with this one. It makes life easier.
With that last point,
Yes.
is that okay? So, what is telling us that then S is a subset of M?
Oh, that's part of the hypothesis.
Oh, that's like part of the givens.
Yeah. So so we've got a subset S that
Okay.
we suspect is the span.
Yes.
If you verify three things, it contains E, it is a subspace, and any subspace containing E contains S, then we can conclude that S is the span.
Okay. So the then is not a conclusional then. It's a
This then is the conclusional.
okay.
This is part of the hypothesis.
Okay. Thank you.
Yeah. Yes. Right. Yeah. So if we were gonna really write this out really this would be like a, you would do like there'd be a lot more quantifiers. There'd be a lot of like backwards E's and upside down A's. Like so, right here, this would be a for all M with this. That's part of the hypothesis. All right, and in fact, we'll use this in a little bit to prove that the span of a set has a much, like I was saying, there's a more like vector space oriented definition for it, and we'll see that in a moment. But before we get there, I want to now use this characterization to prove a whole bunch of stuff about spans, and I want you to keep in mind all these proofs we're about to do right here. These proofs are just going to be like snap your fingers, like boom, 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 boom. I don't know how to snap, but these are all just like you get this stuff for free, and then we're going to prove the more traditional definition of span, and hopefully you're immediately going to recognize that, oh yeah, if I wanted to use that to prove all this stuff right here, those proofs would have been terrible. But anyway, let's do these proofs. These are all just going to be bing, bang, boom, nothing crazy. So, for example, the first one, we're going to prove that if A is a subset of B, then the span of A is a subset of the span of B. Right, so another way of saying this is that span is a monotone operation. So when you're feeding in, right, something being a subset, then that is respected by the operation of span. So let's prove that. So how's that going to go? Well, by construction, we know B is a subset of the span of B, because span is the smallest subspace containing the set. A is a subset of B by hypothesis, which means that A is then a subset of the span of B, and span of B is a subspace. So that means span of A, which is the smallest subspace containing A, has to be contained within the span of B because span of B contains A, and span of B is a subspace. Boom, there we go. Right, so again, this proof here used the characterization that span is the smallest subspace containing the set. So A is in B, that means A has to be in the span of B because B is in the span of B. And span of B is a subspace. Span of A is the smallest subspace, so it's got to be within the span of B. Right. Next up, span doesn't do anything interesting when you apply it to a subspace. And that shouldn't be too surprising. Span is the smallest subspace containing a set. Well, if you're already a subspace, then this shouldn't do anything. So let's prove that. Well, M is a subset of itself. That's always true. You're always contained within yourself. And M itself is a subspace, so that means the span needs to be contained in M, but by construction, M is contained in the span of M, so these have to be equal then. If you've got subset in both directions, that means we have equality, right? Having subset in both directions means that those two sets have the exact same elements. They have to be the same sets. All right. Nice. Okay. So there we go. Span of a subspace doesn't do anything, right? And that makes sense based on our intuition of what span is, the smallest subspace containing the set. If you're already a subspace, then your span must be yourself. All right, now equipped with that, that lets us prove the next thing. Span of a span doesn't do anything interesting. So given a set, you can create its span, but then at that point you can't keep going up. You can't make like a tower of spans. If you take your set and you span it, that's it. So if you apply it again, nothing happens. So this will be pretty easy because we just proved that the span of a subspace is itself. So since span of E is a subspace, applying span to it doesn't do anything. We just proved that any subspace is equal to its own span. So point C, this is for free. We're done. Point B tells us what's going on. All right. Now, two more things. So the first one to prove is that span of a set is contained within two particular sets. Span of E is a subspace, so it's non-empty. In particular, it has to always have the additive identity of a vector space, Z sub 0 sub V. Right, and note, this also is demonstrating something that maybe you haven't noticed, but this is a worthwhile thing to point out. Membership is equivalent to subspace, where on the left you've got the singleton consisting of it. So the set whose only element is 0 sub V, that is equivalent to 0 sub V belonging to the set. So this equivalence is used a couple of times in math. It shows up and it's quite useful. So if you've never really processed that before, put that in your toolbox. That is a tool that is used every so often. All right, and then by construction, span is just a subset of V. So we now have that span as a subset contains this set, and it's contained within V. So that then leads to two pretty natural questions. So span of E always contains the singleton that has Z sub V 0 sub V in it, and it's always contained in the entire vector space. So naturally, you want to ask, well, when do you have coincidence? So coincidence with 0 sub V, so let's say we took the span of our set, and the span is trivial. Right, so the span only has 0 sub V. Well, the only thing that will do that is the empty set, or 0 sub V, the singleton itself. So let's now demonstrate that span of the empty set indeed exists, and it's what you think it should be. The empty set is a subset of anything. I don't care what set you're talking about. And this is another example of like a vacuous truth. Because in order to be a subset, that means every element on the left belongs to the set on the right, but there's nothing over here. So the for all statement is immediately true because there's no way of negating it. Right? There's no way its negation holds. Because this negation would be there exists something in the set that doesn't do what we want, but there's nothing in that set. So that there exists is false, therefore the for all true, the for all must be true. So that's one of those like weird quirks of logic that when you first encounter it, like you might react like, oh, it's so dumb. But it's important. Got it. It gets used. All right. So since the empty set is contained in this set, and that set we proved is a subspace, that means the span has to be contained in there. But as we just demonstrated in V, this is always contained in the span. So we got subset both directions, so we have equality. So it's weird to think about, especially when we're about to talk about the next characterization of span. The empty set does have a span. Always keep that in your head. You can span the empty set. It's trivial, it's just the singleton containing the additive identity, 0 sub V, but it does have a span. And this is one of those, again, an extreme case we need to keep track of. All right. That being said now, let's, now that we've completed the proof of this, let me now set up the more traditional formulation of span and talk a little bit about it. Okay, so here I've got a more useful characterization. Okay, so we are now about to prove that the span of a non-empty set is the collection of all linear combinations of things taken out of the set. So in other words, you belong to the span precisely if I can write you as alpha 1 v1 plus yada 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 plus alpha n vn, where the alphas are just some scalars and the elements are being taken from the set. Right, so if you were to look at your textbook and you were to look at the way they define span, this is exactly how they define span. They say span is the collection of all finite linear combinations of elements out of E. Right, and this is the much more vector space oriented definition for span. But like I said, I like the definition of span as the smallest subspace because that's a much more versatile statement. You can really apply that to a lot of things and get a lot of proofs for free. This is, of course, a more tangible definition, but right, it's a byproduct of the way I think of span, the way you should think of span, that it's the smallest subspace. By coincidence, it ends up being the collection of all linear combinations. But in terms of like how we can prove things with span, it's smallest subspace is the better way of thinking of it. And your textbook does get to this. They start with this definition, show that it implies the other one, the one that I've been using. But like I said, I like that one. It's a better one. It's more versatile, in my opinion. But this one is, of course, more tangible. So anyway, so we're about to prove the following statement. So note what it's saying. It's giving me a characterization of what the span is. Okay. So if you let your mind flow back to our corollary, part D, in order to prove something is the span of a set, you need to do three things. Verify it contains the set, verify it's a span, and verify that any subspace containing E has to have that set in there. So if I want to prove that the span of E is the collection of elements that are linear combinations, so let's start off with that particular set. Define S to be the set of all linear combinations. So here, right, I'm letting S be the collection of all things that can be written as a linear combo of elements out of E. So I want to prove that this is the span of E, so I've got three things to verify. It contains E, it itself is a subspace, and given any subspace containing E, S has to be contained within it. And then once those three facts are proven, then by the definition of span, this set has to be the span. It's the smallest subspace containing E that is precisely the span. Okay. Now, before we end the proof, I want to note something. I want to highlight something in the hypothesis. I have included in my assumptions that E is non-empty. That better show up in the proof. If it doesn't, it's unnecessary. So this is something that I think I mentioned to a few of you who did a pre-screen for your submission. If you don't explicitly use the hypotheses that are given to you, especially on a homework, that means something is wrong. And I think I mentioned it. That's always a red flag. If you see a proof and there was a hypothesis that did not get used, it's either being subtly used or something is wrong. So you always want to, right? If somebody says, "Here's what I'm assuming, and here's my proof," you don't see that assumption, and you're like, "All right, well, why'd you need that?" So this is something to really stress here, and also hopefully it makes sense that we need non-empty. I'm claiming that anything in the span can be written as a linear combination of things in the set. The set was empty. I couldn't do that. So, right, this conclusion would be nonsensical if E was empty. So, it beyond it's needed for the conclusion to make sense. It needs to show up in the proof, right? And it will. And I'll point out exactly where it shows up. Okay, so we planned the work. Let's work the plan. So we need to prove three things. E is contained in S, S is a subspace, and any subspace that contains E must contain S as well. As we noted, this will give me that the span of E is the set S, and thus the conclusion holds. So thus we get a much more useful characterization of span. It's the collection of all linear combinations of things out of E. All right. So first, let's prove E actually has to be in the set S. The set S is the collection of all things that are linear combinations of things out of E. Well, anything in E is a linear combination of things out of E. You just scale it by 1. Boom. Done. This is the easiest part of the proof, by the way. This is just like obviously this works. So, all right, nice. So we now know that E is contained in S. So the first thing is taken care of. Next up, all right, let's prove that S is actually a subspace. Now, in order to prove a subspace, I need to do two things. First, verify that the set is not empty. Okay. And then verify that it's closed under scaling and addition we can do those separately or do them simultaneously. However you want to do it. I'm going to do it simultaneously for efficiency's sake. Right, I'm speed running this proof. That's the that would be a Twitch channel. The speed running proofs. Okay, so first, they need to verify S is not empty, and here is precisely where the non-emptiness of E comes into play. We proved E is contained in S, E is not empty, so S has to be non-empty. If S was empty, that would mean E had to be empty, contrary to our hypothesis. So, there it got used. So hypothesis, I used it. It's there for a reason. All right. So that checks off the first box. S is a non-empty set. Okay. And I really want to stress this too. This is a classic blunder when proving something is a subspace, forgetting to verify that it's non-empty. And that's something, this is like super folklore in mathematics. You always want to demonstrate the sets that you're working with are non-empty. The last thing you want to do is write your PhD thesis about the empty set. That's a legendary thing in mathematics where somebody was defending their PhD dissertation, and some person in the audience eventually raises their hand and says, "Hey, is that set non-empty?" And then it turns out that the set was empty, and oh my god, my entire dissertation is a lie. That's such like there's no way that really happened because you don't get to your defense without knowing your sets are non-empty. That'd be ridiculous. But anyway. All right. So we verified the set is not empty. Now we need to verify that it's closed under the operations. So pick two scalars and pick two things out of S. Let's prove that alpha x plus beta y remains in S. Now, in order to be in S, that means you need to be a linear combination of things out of E. All right, well, x and y are in S, so that means x and y are linear combinations of things in E. Now, note some subtleties here. So X is a linear combo of things out of E. And so is Y, but note, I use different subscripts. We don't necessarily know that it's the same number of things. Okay, and the scalars, we don't know that they're necessarily the same scalars. And likewise, the things, we don't necessarily know they're the same things out of E that make it. We just know that there are these things. All right. Now, let's finish up the proof then. Obviously, if I scale this, and I scale this, and I add it together, well, then I've just got a bunch of scalar multiples of things out of E added up. But let's make it a little bit more formal. Define gamma to be precisely those scalar entities, and from 1 to n, and then we tack on the scalars associated with W. So note here, I got to make the subscripts line up and make everything work. But exactly what I just said, since X is a linear combination of things out of E, B is a linear combination of things out of E, if you scale them together and add them up, you'll get a linear combination of things out of E. You can, of course, get it very precisely, which is exactly what I did here, by giving explicit formulas for what the scalars need to be, and explicit formulas for what the elements out of E need to be. And so you're a linear combination of things out of E, so you've got to be an S, and thus S is a subspace. Right, so you can verify that this is exactly the expression of taking alpha x plus beta y and arrange all the scalars and the elements, and this is what you'll get. So formally, that's what it ends up equaling. So you can film the details. I'm just jumping to it. It's quite clear that X is a linear combination. So if I scale it, it's still a linear combination of things out of E. Likewise, Y is a linear combination of things out of E. So if I scale it, it's a linear combination of things out of E. And if I add them together, you're literally a linear combination of things out of E. An explicit formula here is given, so to really hammer it home. But anyway, it's clear now S is a subspace. So we're trying to prove that the span of a set is equal to the collection of all linear combinations of things out of the set. We're almost done. We've proven that the set of all things that are linear combinations out of the set contains the set. It itself forms a subspace, And now the last thing to prove is that it is indeed the smallest possible subspace you can create. Okay, so take any subspace that contains E. Given anything out of S, well, then it's a linear combination of things out of E. Because you're in E, let's get voice crack right there. Since you are in E, that means you must be in M, because E is a subset of M. And as we proved, any number of things in M, the linear combination of them must remain in there, right? Any subspace, if you take any number of things and scale them up and add them, that will remain in the subspace. That was one of the first things we proved about a subspace. So that means this linear combination must remain in M. So anything that's in S must be in M. And so S contains E. S is a subspace. And any subspace containing E contains S. So S is the smallest subspace containing E. So we have now proven a much better characterization for span. Span is the collection of all linear combinations of things out of E. And there we go. Nice. Pretty good proof. All right, sweet. So we now have a much more useful characterization of span. That the span is just the linear combination of linear combinations of elements out of the set E. That's really nice. Now, in this class, we're going to look at very particular spans. We're going to look at spans of finite sets. So note this definition allowed E to be anything. You can talk about any subset of a vector space. As we set up, R2 can be described using linear combinations of precisely two elements. And that titrates up. R3 can be described using linear combinations of three elements. R4 is linear combinations of four, blah, blah, blah. So we will primarily care about linear combinations of finite things. And for the most part, when you're dealing with linear algebra, you're always dealing with finitely many things. If you're looking at spans of infinite sets, that's when you start getting into functional analysis. You need to start taking limits and things like that. And if you want to talk about that, I can tell you all about it. That's my wheelhouse. It's my favorite stuff. But we don't. We're going to focus on the case of finitely many. So let's get a characterization of the span of a finite set. Okay. So for notational convenience, note that a finite set as a subset is usually written as this, but this is some ugly notation right here. So we're not going to use that. We'll just abbreviate it to this. And this is pretty standard practice when you're talking about the span of a finite set, right? Really, you could drop the curly braces and just make it look a little nicer. This is done a lot too when you're looking at finite sets and you're like applying an operation to them. You drop the curly braces and you just do like, oh, it's a list. All right. So, all right, we will now prove an even better characterization. If you have finitely many things, then its span is exactly the set of linear combos of those exact elements. Now note, the theorem we just proved, that the span of a set is the linear combination of finitely many things, right? That doesn't immediately give me this, because remember, I pointed a subtle point. It gives you the span of a finite number of things. There's no guarantee of how many things come out of E. Here, we're about to prove that if you've got a finite number of things, then the linear combo has the same number of things. Okay. Subtle difference there. The theorem we just proved does not immediately tell me this. So I actually need to do this proof. And actually, if you wanted to use the thing we just proved to prove this, it's actually a huge pain in the ass. So rather than that, I guess you can't. Hopefully, you can't see that. I'm not in presentation mode. I just got an email. Let me close Outlook so no sensitive information shows up. Anyway, all right, yeah. So the theorem we just proved doesn't immediately give me this because the theorem says that there is a finite number that gives you it. It doesn't guarantee how many. Okay. So we got to do this proof, and like I just said, using the previous proposition to prove this is actually like it sucks. So rather than doing that, let's just model the proof we just did for this one. So we'll do the exact same thing. Let S be the thing on the right. We claim that's the span, so prove three things. It contains the set, it is itself a subspace, and finally, any subspace containing the set contains this. Okay, so it's clear that the finite set x1 to xn is contained in S. Fix any number from 1 to n. We can write that as a linear combination of the elements out of the set, where you zero out everything other than the index we're interested in, and then you scale by 1 right there. That tells me that this set right here is definitely contained in S. Any individual element can be written as a linear combination of all of them. You just throw zero scalars everywhere you don't need the element to appear. All right. So boom, there we go. So we've proven that the set in question is contained in S. Right? Because I'm trying to prove that this set S right here is the span of the set. So we need to show that these elements are contained in there. And again, remember when we write span like this, it is abbreviation for this, because span is a property of subsets, not properties of individual elements, even though this notation is making it seem that way. It's not. Span of a set is what we do, not span of individual things. You have to conglomerate them together into a set to talk about their span. All right. That being said, next up, we want to prove that that set is indeed a subspace. We have that it's non-empty for the exact same reason as before. It contains a non-empty set, so it must be non-empty itself. Now let's prove that it is a subspace, so take two elements and two scalars. Well, any two things out of the set are linear combinations. And now note, S here was defined to be linear combinations of exactly n things. So in this case, we don't have that n and m. We know that they're both n in this case. And make this a little bit more precise. These are real numbers. Right, so now the number has to be locked down by definition of S, but right, there's no guarantee the scalars are the same. They could be potentially different scalars, so let's use different symbols. All right, and now if we scale and add these together, then yeah, oh, that's also missing some stuff. God damn it. I'm allowed to swear, it's PG-13. Oh my, oh, blech. Screwing up here. Right, there we go. Oh, I haven't said it yet. I haven't said the I swear to Yeezy. I try to use that in my everyday speech. It's rather than exclaiming Jesus or something, just yell at Jesus. It's a lot funnier, I think. Let's stop there before this gets. Let's stop there before this gets dangerous. All right. Anyway, so we've now proven that S is indeed a subspace. It's non-empty, and any linear combination of things out of the set remains in the set. Subspace proven. All right. Final thing. All right. We've got that S contains this, and it is a subspace. So what have we verified now? We verified that the span then has to be contained in S. So I'm actually going to tweak this a little slightly. Right, what we could do now, of course, is prove that given any subspace that contains x sub 1 to x sub m, S needs to be contained in M and walk away. But we can actually directly prove the equality we want. So let's actually do it that way. So S contains this, and it is a subspace, so the span is contained in it. Take anything out of that set. It's a linear combination of elements out of that set. So since each x sub j belongs to the span, that linear combination needs to be in the span. So we get the subset in the other direction. So here, this proof is slightly different than kind of the one we did. It's still proving the exact same thing, but rather than given an arbitrary subspace showing that S is contained in it, we can kind of directly manipulate it to prove that, yeah, well, the span needs to be what we want it to be. All right, there we go. So we've now proven an even more useful characterization, and one that we're really going to use a lot. Given any finite set, its span is just a linear combination of the things in the set. Sweet. All right, so now that we've got that proven, let's go back to reality for a moment. Let's move away from super theoretical stuff and look at some explicit examples so we get a real good feel of how span works. All right. So like I just said, now that we have all this stuff proven, computing spans now is super easy. Just figure out what the collection of all linear combos look like. And especially if I want to do a span of a finite set. So, hey, here is a subset of R3, 0, 1, 0, 2, 0, 1. I want to figure out what the span of this set is. Okay. The span is the smallest subspace containing this, and as we just proved, it is the collection of all linear combinations. So any element in the span of this has to be scalar multiple of the first plus scalar multiple of the second, and if I put those together, I get this. So that means I can tell you that the span of that set is the collection of all vectors that look like this. And that's it. Furthermore, note something here now. For your homework that you just submitted, I said, hey, prove the following thing is a subspace, right? Specifically, the collection of elements of R4 that look like A, B, C, A minus 2B plus C. There was a much easier way of proving that. It's super easy to prove that that's a span of a very particular set, and spans by construction of subspaces. So there's a super easy way to do that homework problem now. Now that we know what spans are, but I made you do it directly because this is just what you do in math classes. You just get hazed all the time. It's like, hey, do it like this, and it's like, oh man, that sucked. And then the next thing you do is like, hey, there was an easier way to do that. That's for you've got no, that, and I'm sorry to tell you, that never ends. That just keeps going and going and going in every math class. So it's like you do something and then it's immediately followed up with there was an easier way to do that. That continues on even in grad school, like in grad classes. It's just like math is like a never-ending like parade of like, okay, here's how you do this, and then like you pull the curtain and you're like, oh, there's an easier way. It keeps it just go it won't stop. It never ends. Never, yeah. Well, right. So actually, never-ending magic trick. That's a good point. There is a non-trivial overlap between mathematics and magicians. So unfortunately, I don't know if you know, Ron Graham passed away recently. If you don't know who Ron Graham is, very famous mathematician. You may have heard of something called Graham's number. It's like the biggest number ever seriously used in a mathematics argument. That's kind of not true. There are bigger numbers that are known now. Busy Beaver of 4 is so gigantic that not only you can't even like Graham's number is humongous to the point that even if you were to like convert all the matter in the known universe into pen and paper, you still wouldn't be able to write it, the complete number. It's just like so gigantic, but there's still like we've got an understanding of like how there's a way of describing how big it is. Busy Beaver of 4 or Busy Beaver of 6, I forget which one that is. It's so gigantic you can't even compute it. There's like no way of even like coming up with like you couldn't even write it down. It's that big. Anyway, anyway, yeah. So mathematics and magic have a non-trivial overlap. Ron Graham was like the quintessential like mathematician kind of guy. He was an expert in juggling. He always was able to like turn all these really complex math ideas into like card tricks and other cool stuff. So he passed away like a month ago, I think. He was in his 80s, so not too surprising. And we here at Iowa State have a non-trivial connection to Ron Graham. Steve Butler, who at this point I would probably say Steve is probably the most famous math person at Iowa State. Generally speaking, if we're talking about like our alumni who are most famous, Bill Johnson is probably the most famous like mathematician in terms of like theorems he's proven. But Steve at this point is probably Steve is a nerdish number one, and Steve worked a lot with Ron Graham, specifically Ron Graham's wife Fan Chung is a Steve's PhD advisor. So I should probably call him Professor Butler. Anyway, but yeah, so where math is a never-ending math trick, the goal of a magic trick is to hide what you're doing, and that's the problem in math. We want to know how you're actually pulling it off. So that's why it keeps just like descending in the madness of like, I did this magic trick. Well, how did that work? Well, it was really this. And if you do it that way, it's easier. It's like when we make you do the limit definition of the derivative. And that's like, there's easier ways of doing that. So, sorry to say that the curtain just keeps pulling back in mathematics. All right. That being said, let's have some more fun with span to wrap things up. We still got about 4 minutes. So let's look at the following finite set, 1, 0, 1, 1. I claim the span of this is all of R2. And the language we use for this is that E spans R2. So if you ever see somebody saying this set spans this vector space, that means that the vector space can be written as a linear combination of things out of that set. So how are we going to prove this? Okay, we'll take anything out of R2. I'm going to show that I don't care what you took out of R2. I can write it as alpha 1, 0 plus beta 1, 1. Okay. So specifically, I need to construct for you alpha and beta that do that. Okay. So set it all up. So X is an element of R2, which means that it's an ordered list of two things, X1, X2. I am going to show you how to find alpha and beta to make this work. So specifically, I'm going to find alpha and beta so that X can be written as alpha 1, 0 plus beta 1, 1. Now note that if I combine this together, that gives me alpha plus beta, beta. And, oh, hey, look, it's a system of linear equations. Oh boy, it's almost like all of this is eventually just this stuff in disguise. Like I said it was going to be. All right. So in other words, I've got the following, and I want to solve alpha and beta in terms of x1 and x2. And this one's super cheap because beta is automatically x2. Plug that in. Blip. There you go. You're done. Alpha has to be x1 minus x2. So there we go. Any element out of x can be written as a linear combination of 1, 0, 1, 1. The constants have to be these. There we go. That's pretty cool. All right. So one last thing to finish up the conversation for today. If you look at the set of polynomials, and if you look at this particular subset, the collection of the polynomials 1, x, x squared, x3, span of that by what we proved is equal to that stuff. And oh, hey, that's R3. R sub 3, the collection of all polynomials whose degree is less than or equal to 3. So for your homework, one of the problems you have to do. One of the problems is proving that a particular set of polynomials spans R2. And basically, it's kind of like what we just did, but you do it in R2 instead. So that's pretty nice. All right. So we've now seen a couple of examples of things that span vector spaces. So R2, as we started off this whole conversation, is spanned by 1, 0, 0, 1. Everything of R2 is like trivially a linear combination of those things. But there are other sets that span them, as we just demonstrated. Our favorite sets of polynomials can get spanned by some pretty obvious sets, and as you'll prove for homework, there are other sets that span them. The natural next question is, all right, out of all the sets that can possibly span a set, are there ones that are better than others? The answer is yes. And I don't want to hide it. I guess we're going to talk next time about linear independence, which you may have encountered before. If you haven't, though, basically the gist of it is, well, when I'm looking at spanning a set, I want to span it efficiently. I don't want redundant information, and the linear dependent sets are precisely the ones with redundant information. We'll make that a little bit more rigorous and have a nice definition and prove that linear independence goes the way that we want that intuition to follow. That will be next time. That is it for today. Thank you for joining. You're free to leave. If you got some questions, you can hang around and ask them. Otherwise, that's it for today. And I'll see you tomorrow straight out of my basement.